All right, well, welcome to the end of a short week here in calculus. Hopefully quiz 2 went fine. We'll of course go over that next week. But anyway, today's plan, we're going to go ahead and pick up where we left off, keep looking at integration, and specifically we're going to look at the inverse trig functions, right? Because so far we know how to deal with polynomials, we know how to deal with, trig functions. We now have all of the trig functions, sine, logs, and exponents. So we're going to look at inverse trig functions, and specifically the kinds of things that lead to inverse trig functions. So yes, I will remind you all about them and how they work, because I imagine most of you don't remember the derivatives even of the inverse trig. So we'll start there just as a little recap and then move forward. But before we do that, just curious if anyone has any questions on the homework, anything they'd like to see or talk about that we've been working on this past week. All right, so Chase just put in the chat box a couple of problems here, 8 and 17 from 1.6. All right, thanks, Chase. And Lexi, when you say 9/12, do you mean 9 or 12? 9 and 12, okay, from 1.6 as well. All right, so I've got on my list from 1.6, 8, 9, 12, and 17. So let's go ahead and go take a look at those and see what we can do. So I'll go ahead and share my screen. I will try to share my screen. All right, so exercises 1.6. As we wait and wait. All right, finally. So let's go take a look at number 8 first. Down here. All right, so it says, consider the integral cotangent times natural log of 2 sine of theta. All right, so it says this can be transformed into a basic integral by letting u equal what? And then after performing the substitution, what does the integral look like? All right, so for this one, what do you guys think? What would be a decent choice for you? Or what would you want to try?
The natural log of 2 sine theta.
Okay, so the natural log of 2 sine theta, the whole thing, or just what's inside?
Yeah, the whole thing, because I remember this question because I first only thought it was a sine, but then it kept like rejecting it, and then I figured it out with the natural log.
Okay. Mm-hmm. Cool. Well, let's go to a whiteboard real quick and let's kind of work this sucker out, because this is one where probably, well, let me write this out first. So we're looking at the integral of cotangent plus the, or not plus, times the natural log of 2 sine theta. Okay, now, most likely, and I would not be surprised at all if some of you started with, let's try doing a u substitution, but let's let u equal 2 sine of theta. right? And in fact, Susanna, right, this is what you said you started with. You tried this first. And this makes sense, right? Because then we've got natural log of u and everything is good. Well, let's see what happens if we choose that. So we're going to go du equals. So the derivative of 2 sine theta is 2 cosine theta times d theta. And now we need to start substituting in. Okay, so if I solve this for d theta is du over 2 cosine theta. That's what I'll put in there. So let's see what happens as we start changing this. There's still the cotangent. We'll just leave that for right now. And now we got natural log of u. Okay, that's cool. I like natural log of u. And then d theta is du over 2 cosine theta. But we have all kinds of theta stuff still remaining, which is a bit of an issue, right? We got to get rid of all that stuff. All right. So here's what we can do. Let's use the trig. Let's use identities. Cotangent is cosine over sine. It's supposed to be a c, not los theta. Cosine theta. And you can see now that the cosine thetas are going to cancel. So we'll go ahead and slash those guys off. So we're feeling better, but we still have the sine of theta. But we can actually replace that using the substitution up here, right? Sine of theta is actually equal to u over 2. So if we go and we put that in, we're going to now be all in terms of u. So we got natural log of u divided by, well, we got the sine of theta. Well, there's a 2. Let's put that there first. And then sine of theta is u over 2 du. The 2's cancel. And we're left with the natural log of u du over u. So if we were to pick that as our u, here's where we are. And the problem is this is not a nice form, right? So we went through all of that and we got here. And this is when you go, well, crap, what do I do? Well, I'm going to show you that this is still salvageable. What we can do is actually another substitution. So let me just call it P, let's say. If I let P equal the natural log of u, then dP is 1 over u du. And hopefully you notice the 1 over u du is right here. So if I were to change this into an integral of p's, this is now going to be the integral of p dp. Oh, good Lord. But this is now easily integrable. This one's p squared over 2 plus c, which now just means go and plug in, right? We'll plug in our p, which is natural log of u, plug in our u. And what we end up with, if we resubstitute, is the natural log of 2 sine theta squared over 2 plus c. All right, now just some things about this one. I know that starting with this one, it just crushed everybody, right? You're all like demoralized now. Let's just analyze this and look at what's going on. So first things first, sometimes when you pick a substitution, it will lead to requiring another substitution. That happens. I mean, you saw that when we differentiated, think chain rule, right? Chain rule didn't always have just 2 pieces. Sometimes it had 3 or 4, depending upon how many compositions were going on. Well, if that happens differentiating, that's going to happen integrating. So Be aware that this will happen sometimes. All right. However, when this happens, sometimes you can take care of it all at once. So you may recall that when I first asked for a u, Susanna said the natural log of 2 sine theta, right? Putting it all together. Let's see what happens if we actually do that instead. So erase this substitution because we're going to try the one that Susanna suggested first, even though that was actually her second substitution, I think she said. So instead, let's let u equal the natural log of 2 sine theta. Now when we differentiate, remember with natural logs, you take what's inside the log and put that on the bottom. And then you take the derivative of what's inside and put that on the top. Well, the derivative of what's inside is 2 cosine theta. So we get du equals 2 cosine theta over 2 sine theta d theta. Obviously the 2's cancel. And if we remember our trig, cosine over sine, oh look, that's our cotangent. So if you come back over here and you look at this integral, if I now turn that into the u's, I've got the natural log of u, the natural log of 2 sine theta, that is my u. And then the cotangent d theta, those are all du. All right, so had we seen that, this substitution lets us do it in one step. Because look at these two integrals. Look at the blue one that we just did here. And look at the orange one that we got after we did the 2 substitutions. They're exactly the same form. So basically, we just did both steps at once. So this becomes u squared over 2 plus c. We plug in our u. Well, that was that natural log of 2 sine theta. And you see that we're exactly at the same place we were before. We were just able to do it in one step. Okay, so I think the moral of the story on this one is twofold. One, if one substitution doesn't work, allow yourself another. And I think more importantly, though, is that sometimes the u, the better choice for you, isn't the more obvious choice for you. Because like I was saying, I think for the most part, people would look at this and go, yeah, naturally the choice for you is the 2 sine theta. It just turned out that if we include the natural log, it was a little bit quicker. All right, so how do we feel about 8? It's a little bit tricky for sure, but definitely doable. All right, let's go take a look at number 9. All right, so next one here. So 9, we've got natural log of z to the 7th, dz over z. And so again, this is, let's transform this into a basic integral. All right, so looking at this, what do you think you want your u to equal? All right, thanks, Bruno. Just put in the chat box natural log of z, and I definitely agree. Because if you look at this one, remember what we did last time was sort of start at the very interior. If I substitute inside the natural log, I'd be saying let z or u equal z, but that's a never do that substitution, by the way. Never just substitute in for the variable because you're back to exactly the same form. You just change the name, it doesn't change the structure. So instead of that, we see that the natural log is in another function, it's being raised to the 7th. So I would definitely, in this case, let u equal natural log of z. So this will look like u to the 7th. And that'll be easy to integrate. We still have to deal with that z, but when you differentiate natural log of z, you get 1 over z. And so this guy ends up being part of the du. So when you end up doing that substitution, this just becomes the integral of u to the 7th, which is pretty quick. All right, so it would be u equals natural log of z. Let me just, I might as well get some points here because I never get points. So natural log of z. So then du is going to be 1 over z. And then it leads the integral. What did I say? Z to the 7th. Right. So, oh, except not z. How about u to the 7th? All right. So, okay for number 9, or at least this form of number 9. Yay, green check mark. Okay, so let's go look at 12 and 17. So number 12.
I think 12 is the same now that you showed that.
Okay, yeah, so 12 is virtually identical. Actually, it is identical for the u and the du parts. Just notice that this one doesn't have a dz on the outside of the box, so make sure you put the dz in that box as well. Okay, cool. Well, that was like a twofer then, right? So let's jump down to number 17. Oh, last one must be hard. All right, so we've got 1 over 6 plus e to the minus 8x. All right. So the question is, what do we do for the substitution there? So let me go to the whiteboard, because this one we're definitely going to have to work out. We can't just talk it out. I'll clear all my drawings here and we'll start fresh. All right, so we've got the integral of 1 over 6 plus e to the minus 8x dx. All right, so let's start with u equals. What are some choices for u equals?
Six plus e to the negative 8x.
Okay, so that's one choice. I'm going to make a list of all kinds of different things we could choose. So we could just take the entire bottom and make that our u. All right, here's another choice. What if we just let, okay, thanks, Mariola just said, what about u equals minus 8x? Then we have e to the u, which is definitely a better form. And then there's one other that could potentially work. So I'll put it up here as well. It would be if we let u equal e to the minus 8x. So I would say, looking at this, that these are our 3 real options. The minus 8x should be a pretty obvious one, because that would make this e to the u. The 6 plus e to the minus 8x may not be quite as obvious, but that's definitely a nice form. It's going to give us 1 over u. I like 1 over u. The e to the minus 8x may not be, that's probably the least obvious. Now it's going to give us 1 over 6 plus u, which we can anti-differentiate. We know that's going to give us a log form. So it really all depends on what the du ends up being for these and what that form turns into. So I'm going to actually walk through all of them. I'm going to start with this guy just so I don't have to change the color on my pen. But the derivative of e to the minus 8x is going to be a minus 8 e to the minus 8x dx. And so the dx then is going to be du over that. So we get du over minus 8 e to the minus 8x. And I'm going to substitute in my e to the minus 8x here to get minus du over 8u. So that's actually what the dx equals. So if you're curious about where the hell that u came from, that was this. All right, so if we substitute all this stuff back into the integral, we're going to get integral of 1 over 6 plus u times du over u, and I'll pull the minus 1/8. All right, so that's what this one looks like. I definitely don't want to do that as my substitution. We don't know how to integrate 1 over 6 plus u times u yet. So while that's a possibility, it's definitely not one I would pick. So let's look at what happens if u is equal to minus 8x, then du is minus 8 dx. So if I substitute in here, I'm going to get 1 over 6 plus e to the u times du, and there's the minus 1/8 out front again. All right, well, this form also doesn't really look that good because we don't know how to do 1 over 6 plus e to the u. In fact, I think I would rather have this kind of purplish form than the green form, because at least this is just polynomial stuff. All right, well, let's see what happens if we use this as our u. So then du is going to be minus 8 e to the minus 8x dx. So dx is going to equal, again, minus 1/8 du over e to the minus 8x. All right, so let's substitute this stuff in. And we're going to get the integral of 1 over u, with all this. And then the dx, we're going to get minus 1/8 du over e to the minus 8x. But we're going to have to substitute that again. And if we solve for e to the minus 8x, we get u minus 6. So this is minus 1/8, the integral of 1 over u times du over u minus 6. So hopefully everybody saw where that came from. That was the whole thing. Subtract 6 from both sides here. Get e to the minus 8. All right. Well, if you look at this pink one versus the kind of purplish one, they're pretty similar. They're really the same kind of structure. And I want to apologize for this one. This one, we don't have a technique for yet. At least we haven't talked about it. I don't know, did anybody see what to do on the next step, or did you, when you got to this, just go, we'll ask Bruce? Anybody have an idea what you could do at this point?
Sub back in.
If we were to substitute back in, it's just going to bring us back to the original integral. So we don't want to do that, right? We always want to save the substituting back in for after we've gotten our antiderivative. But we don't have an antiderivative yet. All right, so here's what you can do. You can use algebra. I know it's everybody's favorite. But let me, I'll go ahead and run with the pink one since it's pretty much equivalent anyway to the purple one. Okay, so here's what we're going to do. This is going to be what we call partial fraction decomposition. And if you all just want to, wait, what now? This is something that we often do in algebra, where if we have a fraction 1 over u times u minus 6, we're going to be able to break that apart into two fractions. And those two fractions have the factors of the denominator. This is really a byproduct of adding fractions. When you get a common denominator and put it together, we're basically breaking it apart. So if you look at this bit on the right, this is the same as a times u minus 6 plus b times u over u times u minus 6. So what we know, if these fractions are equal, since the denominators are the same, the numerators have to be the same. And we can actually use this to solve for a and b. Because if you distribute through, you're going to get a plus b times u minus 6a equals 1. And so if we equate like terms on either side, there are no u's. So that tells me that a plus b has to equal 0. And the constant is minus 6a. So I know that minus 6a has to equal 1. And so I've got a system I can solve. This one tells me a equals minus 6. If I plug that into this other one, it tells me that b is equal to 1/6. So I have no idea, because I can't see most of your faces. I have no idea if this even rings a bell. If it doesn't, well, you should probably go back and find it in pre-calc. But also, we will talk at length about this. We'll talk a lot about the partial fraction decomposition way of solving integrals later. Okay, so if you don't see it right now, that's cool. We'll address it in depth later. But I just want to do this so that we can be complete with this problem. So basically what we just did was we turned it into an integral of two fractions that are being added. So we have a times u, so that's minus 1/6 times 1 over u. And the other one is b over u minus 6, so that's 1 plus 1/6 times 1 over u minus 6. And these we can integrate. They're going to give us natural logs. I mean, I pulled a 1/6 out. I'll even pull a minus 1/6 out just to bring that all the way out front. So we get 1 over 48 times the integral of 1 over u minus 1 over u minus 6. And this one we can anti-differentiate. 1 over u is the natural log of u. The u minus 6 gives me the natural log of u minus 6. And now it's just a matter of plugging our u back in. So we want to run back up to this. Take that guy and plug him back into, oh, can't forget our plus c. Oh, so I apologize for this one. I do not construct these homework sets. So the fact that they gave you one that requires this horrible algebra, that was definitely not my intention with this one. But you can see that we actually do get our answer, right? It's going to be 1 over 48. And just for the sake of space, I'm going to combine it into one log since it's being subtracted. So I've got 6 plus e to the minus 8x divided by u minus 6's e to the minus 8x. And yes, there's algebra you can do to simplify and whatnot, but I'm just looking for, I'd be looking for something like this. All right, so those of you who've been in my classes know I say this all the time. For those of you who are relatively new to me, I will tell you because you're going to hear it a lot. Calculus is not hard. That's a misconception. Calculus is not hard. What makes calculus hard is the algebra. Like you might look at this problem and go, oh no, this is an example of where calculus is very difficult. And that's false. If you actually look at the calculus steps, I mean, check this out. Here are your calculus steps. Right here was a calculus step. How hard was that differentiation? Hopefully you all agree that it was pretty easy, right? There was a calculus step. All right, algebra, 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 algebra. Oh, hey, here's another calculus step. When we actually anti-differentiated 1 over u and 1 over u minus 6. Again, how difficult was that? Well, harder than the first calculus step, but still not bad. So think about all of the work we did in here. The calculus was the easy part. That was the part we didn't even really think much about. Everything else was algebra. So don't go around telling people how hard calculus is. You can talk about how hard your homework is, that's fine. But don't be saying that calculus is hard, because calculus is not hard. What's hard is remembering and using all the algebra from forever ago. All right, so I don't know if this made anybody feel any better about this. I think it was Chase who asked about it. At least you can see how to get to an answer. But unfortunately, it still requires a lot of work, right? And in fact, I'm going to show you another way to do this one today. Hopefully we get to it. I don't know. We're down to only like 20 some minutes, so we'll see where we get. All right, so exponents and logs, exponential forms are really nice. Log forms are also pretty good. They are what they are. Okay, so I'm going to jump up to the main whiteboard and we'll talk a little bit about inverse trig functions. So I'll be right back with you. All right, sorry about that earthquake. That would be I caught the power cord on the way up. All right, so let's talk inverse trig functions. And before we get to any kind of anti-differentiation or anything like that, I want to remind you about the derivatives of the inverse trig functions. All right, so for example, what if we wanted to differentiate inverse sine? So hopefully you remember what the inverse trig functions are, right? They're the functions that we plug in the value of the trig function and it gives us the angle in the right interval, right? But it gives us angles. So these return angles. But we differentiated them. We learned how to differentiate them. We had to use the inverse derivative stuff, right? How they're related, how the derivatives of inverses are related to get there. But this was one of the functions that you learned how to differentiate in Calc 1, or should have learned how to differentiate. So I'm just curious, does anybody remember the derivative of inverse sine? All right, so Susanna, I think she was probably already hit enter on the chat, had already typed it in. I was just waiting for me to ask the question because that was pretty fast. So it's 1 over the square root of 1 minus x squared. Now, I don't want to talk about where this came from because that's not really relevant right now. It's just that this is the derivative of inverse sine. We also had the derivative of tangent, of inverse tangent. This one's the easiest to remember. It's just 1 over 1 plus x squared. It's actually a really nice form. I mean, relative, right? And then the other one that we're interested in is the derivative of inverse secant. And it was 1 over the absolute value of x times the square root of x squared minus 1. All right, so these are just, those were the derivatives of inverse sine, inverse tangent, and inverse secant. There are also derivatives for inverse cosine, inverse cotangent, and inverse cosecant. The only difference is that they all have a minus sign on. All right, so that's why I'm not going to bother putting them up. But if you want, for completeness, slap a minus sign on all those and you get the other inverse trig function. Okay, so if this is the derivatives, obviously, in terms of integrals, if we go the other direction, if I were to say integrate 1 over the square root of 1 minus x squared dx, I'm going to get inverse sine. If I integrate 1 over 1 plus x squared dx, I'm going to get inverse tangent. And if I integrate 1 over the absolute value of x squared minus 1, I'm going to get inverse secant. Okay, so just like all the others, we want to think about going the other direction, taking the derivatives and going backwards because we're anti-differentiating. All right, so think about what this does now. This actually opens up the potential for getting integrals of all kinds of other functions. Like this one right here, the inverse tangent, this opens up more rational functions, functions that we didn't already know how to do. They can't be dealt with just a simple u substitution. Similarly, this one now, with the inverse sine, if we've got square roots in the bottom, sometimes you can do a u sub, but sometimes you can't. This is going to help us for those times we can't, right? So on and so forth. All right. However, it's very rare to have it in exactly this form, right? I mean, this is great for 1 over 1 plus x squared, but what if it's 1 over 9 plus x squared? Or what if this is 1 over square root of 3 minus x squared? Or, right, what about variations on it? Well, if you look at it generically, if you just sort of do the generic approach on these, here are your inverse trig integral formulas, the things that lead to inverse trig. So these are the ones that you're going to want to know. So instead of 1 minus x squared in the square root, we're going to make it a squared minus x squared. So this will allow for something that's a little bit different, like 9 minus x squared or something like that. Its antiderivative is just the inverse sine of x over a. Now, where that comes from is from algebra. I'm not going to do it to you, but you'd factor out the a squared and then do a u substitution and blah, blah, blah. We're just going to learn this formula. You can just trust me. Or if you really want, come to an office hour sometime and we'll derive them all. We'll have a grand old time. All right, so that's the generic form for this one. For the inverse tangent, what we're going to do is we're going to make it a squared plus x squared instead of 1 plus x squared. And if you do that, its antiderivative is 1 over a times the inverse tangent of x over a. Again, that 1 over a is going to come out when we do the algebra. All right, so I think you're starting to see the theme. So for the inverse secant one, we're going to do the same thing where we make it square root of x squared minus a squared. And you'll notice that I did drop off the absolute value here, because when we anti-differentiate, we're not usually anti-differentiating absolute value functions. We're doing with them that don't have that. But as a consequence, when we go and we get our inverse secant, well, we're going to get 1 over a. We're going to get secant inverse, and the absolute value shows up on this side. All right, so there's still the absolute value, just we make sure we put it on the inside of the inverse secant. All right, so as always, I'm going to put a box around these, because these are the important guys. So if we ever have something of any of these three forms, when we anti-differentiate, we're going to get inverse trig. So let me show you how this works. It's actually pretty easy. You just have to recognize the form and figure out what's your A. All right, so for example, let's say we've got the integral of dx over the square root of 4 minus x squared. So I just want to anti-differentiate this function. So if you look at the forms over here, you can see that that's actually very similar to the first one. Right? We've got our 1 over square root of something minus x squared. So what I'm going to do here is I'm just going to write down below that the 4, this is the a squared. So a is equal to 2. So that means that the antiderivative of this is the inverse sine of x over 2 plus c. All right, well, there you go. This thing led to inverse sine of x plus x over 2. All right, so here's another one. What if I've got dx over 2 plus 9x squared? All right, so you look at your forms, and you see that this one looks a lot like the middle one. Right, but there are a couple of issues. One, I don't have just x squared. I've got 9x squared. So I have to adjust this slightly. So here's what I'm going to do. I'm going to do an algebra step. I'm going to divide out a 9 from the bottom, meaning I'm going to factor. So I'm going to write this instead as dx over 9 times 2/9 plus x squared. So I just divided out a 9 in the bottom. So that 9 comes out front. It's no big deal, right? We like constant multiples. So this is going to be 1/9 the integral of dx over 2/9 plus x squared. And now if you look at this form, these are exactly the same. What does a equal in this case? Right, we need to know that a so we can plug it into the formula. Okay, so Mariola just put in 2/9. That's not quite right. That 2/9 is a squared. So yeah, we need to take the square root of that. So we've got a squared equals 2/9. So a is the square root of 2 over 3. So just remember that that thing is a squared. So we have to take a square root. You've seen that a lot. Like think about when you're dealing with circles or something. The radius wasn't what was on the other side. It was the square root of that. Same kind of deal here. All right, this isn't our a. It's the square root of this is our a. But now we can put that in. So we know then that this is going to be 1/9 for that times 1 over a. So 3 over root 2. I just went ahead and flipped it over because of the fact that it's a fraction, 1 over fraction, times the inverse tangent of x over a. So I'll do the same thing, flip it over. So there's the antiderivative of 1 over 2 plus 9x squared. And yes, I can simplify. I'm not going to be too concerned with that, right? So the trick with all of these is to make them look like the form. You want to make them look like the form. Sometimes it requires a substitution. Sometimes it requires algebra. It just really depends on what our function is that we're trying to anti-differentiate. All right, so let me show you some of the ones that require more algebra, some different kinds of substitution, just to make it so that you're prepared for those that are a little more complicated. Because if I just show you the easy ones, then so what, right? Not super useful. All right, so how about this guy? Let's try to anti-differentiate 1 over the square root of e to the 2x minus 1 dx. All right, so looking at that, even if we weren't talking about inverse trig functions, looking at this, you probably think you want to do a substitution, right? Substitution seems like a pretty obvious thing to do. And we could do that, and we will do that. But it turns out the substitution we're going to use, and this might feel a little surprising, is u equals e to the x. And I know that you probably would try u equals e to the 2x minus 1, but you'd see that kind of doesn't take you down a good path. But watch what happens if we let u equal e to the x. So then du is equal to e to the x dx. So dx is du over e to the x. And I'm going to go ahead and replace that e to the x with a u, because I know I'm going to want to do that anyway. So we played that trick just a little bit ago, right, where we substituted in again. All right, so watch what this turns into then. We now have 1 over the square root of u squared minus 1. If e to the x is u, then e to the 2x is u squared. And then dx is du over u. And this is exactly the form that gives us inverse secant. So this guy is going to end up being inverse secant of the absolute value of u plus c. Right? In this case, a is equal to 1. 1 squared is 1. All right, so a is equal to 1. So all the a's just go away. All right, but let's plug back in our u. So we're going to get inverse secant of e to the x plus c. So it turns out that using u equal e to the x made this a really simple form, even though it wasn't necessarily the substitution we would immediately think. All right, so what's on this one? No, we're good. All right, so sometimes the u substitution is necessary to get us into a form where we've got where we're good to go. All right, but there's definitely more algebra we can do to help us with these guys as well. So let me show you one more before we call it a day. I'm definitely going to show you some more on Monday, but let's try one more. So I'm going to go ahead and erase this because I'm sure you've got your forms down and we can figure out where we need to be. But suppose that we want to integrate this guy. Let's say we've got the integral of dx over x squared minus 4x, plus 7. No, this isn't the one I want to do. Hold on. We'll do this one. We'll do that one next time. Let's look at x plus 2 over the square root of 4 minus x squared. Okay, so we look at that, and maybe you see a little bit of inverse trig in there. Like, what about this is relevant to the discussion of inverse trig? Which of the inverse trig functions has this kind of form in it?
Inverse sine, but with no plus 2.
It's definitely looking a bit like inverse sine, because we've got the square root of a squared minus x squared on the bottom, but it doesn't look quite exactly right because of the x plus 2 on top. Okay, well, here's where algebra is going to come in and help us again. I'm going to actually split this into 2. So that I've got x over the square root of 4 minus x squared plus 2 over the square root of 4 minus x squared. So I just split apart my fraction. And now it's definitely looking more like the inverse trig, right? Like, look at this last one. This last one's going to be pretty easy. I've got the 2 on top. That's a constant multiple. So that's just going to go along for the ride. So I'm going to put here plus 2. This is going to lead to an inverse sine. And we're going to get inverse sine of x over 2, right? Because the a was 2. 2 squared equals 4. So by splitting it apart, that second one just immediately became inverse sine. Okay, so then what about the first one? So again, you're thinking, all right, we got that square root of 4 minus x squared. That's going to give us an inverse sine. And that's actually not true at all. this is not going to lead to any kind of an inverse sign. Yeah, Stephanie, good catch. This is going to be a U substitution. This is one you could have done even before I showed you inverse trig functions. Because with this guy, if we let U equal 4 minus x squared, then du is minus 2x dx. And notice that the x with the dx is already part of this. So if you change that using u sub, this becomes the integral of minus 1/2 du over the square root of u. So I like showing this one because it helps remind you that sometimes the easiest way to do it is with our simple techniques, and substitution is a very simple technique. So if we integrate this, right, this is u to the minus 1/2, it becomes u to the 1/2 divided by 1/2. So this becomes negative square root of u. So if we substitute back in our u, we get negative square root of 4 minus x squared. The other piece was 2 sine inverse of x over 2 plus c. And so there is the antiderivative of x plus 2 over square root of 4 minus x squared. So it actually led to inverse trig, but also we needed our previous method as well. Okay, so take from this a couple of things. One, don't forget algebra. I know you don't want to do it. I know you don't want to do it. I totally understand because algebra is a pain. But sometimes the algebra is necessary for us to get it in a form where we can do the calculus. Okay, so be willing to do the algebra. And there are no shortcuts. That's always the other question. Is there a faster way? No. Sometimes algebra is algebra. You got to just suck it up and do it. All right, so, and this is one of those cases. So watch for your algebra, because algebra is going to help. And the other thing I want you to get from this is, again, just because it looks complicated doesn't mean that it needs complicated stuff to solve it. Sometimes you can go back to nice, simple U substitution. Okay, so I definitely want to show you a few more examples that require using algebra. Specifically, I need to remind you about completing the square. And if that just sent shivers down your spine, yep, we're going to have to complete the square. So I want to show you that. So what we're going to do on Monday is I'm going to start with a couple more inverse trig that require some completing of the square, just so you can see that. And then we'll move into chapter 2. We're already there. We're already ready to move into chapter 2. We're going to start applying this stuff. We're going to start looking at some of the other things other than just area under a curve. Some of the other things that we can do with integrals, because we want to give you got to give you a taste of why are we doing this. Like, yay, we're finding antiderivatives. We can do this all day long, but why? We'll start addressing more of that next week. Okay, so that's my plan for Monday. Also want to remind you that there are homeworks that are due Monday night at midnight, including the section on this inverse trig. Definitely work on that over the weekend. We'll see how everybody's feeling on Monday. I'll probably be willing to extend it, but we'll see. We'll see what kind of mood I'm in come Monday. Anyway, so get in there, work on your homeworks, and other than that, have an awesome weekend.
Bruce, can I ask you a question about the quiz?
Oh, hold on one second.